Sundaram. Can you got it? Yeah, I got it. And also a paper that we published in October, and it's mostly about the holographic version of what we are doing. Okay, so what's the outline of the talk? So in the beginning, I will give you some introduction about nearly critical systems and nearly critical superfluids from the statistical physics point of view. And then I'm going to motivate two different things. So the first one I want to motivate is that they are very interesting, and they are probably also worth examining within more modern contexts of studying statistical systems. And then I'm also going to tell you that if you take an oversimplification of what's actually happening in these statistical systems, you're actually ending up describing classical black holes. So there will be two sides. I think I will focus mostly on the field theory constructions, and then I will conclude and tell you what some of the future plans. So what is the motivation behind looking nearly critical systems? So at strong coupling, you often have no quasi-particles. So you might, if you're interested in large distances in a system, then you can look at universal sectors. For example, you can look at the dynamics of conserved charges at long wavelengths. And you know basically that these will be conserved quantities. And so at long wavelengths, they should have some pretty universal behavior. If you have a broken phase in your system, similarly, you have to take into account the Goldstone modes in the system, which fall in the same category with conserved charges, and they will dominate the long wavelength physics. Now, why are phase transitions interesting? Well, close to the first transition, you have what is called the correlation length. This is all that matters close to the phase transition. And you might wonder what is happening exactly at the critical point where this correlation length becomes infinite, and you expect the system to be described basically. So all scales are washed out. There is no scale in the system. So you might expect that there is some power law behavior that dominates your system in that case. So, and I want to examine, well, I will tell you that there is interesting stuff happening from the hydrodynamics point of view when you approach the critical point. And there is a signal that there is some mode there that you have excluded from your system when you were discussing things from the purely hydrodynamics point of view of the broken or of the normal phase. And finally, I will use holography to carry out some microscopic computation. It is a simplification, a great simplification, but there is actually physical systems which are actually described by this simplification, and this is black holes. So if I imagine that I could solve the field theory problem, then I would like to consider a relativistic field theory that simplifies things with some global U1 symmetry, and that the system is at finite temperature T and chemical potential mu. And this is a very difficult problem in general if you start from the microscopic description of the system. But I'm imagining that there is some charged microscopic operator, which transforms globally under U1. And that as I'm changing the temperature of the system, there is a critical temperature below which this operator takes some non-zero expectation value spontaneously. And also I can deform this theory with external gauge fields and also external sources for this charged scalar. I can vary the generating functional of this field theory at finite temperature. I imagine that I can extract the webs of interesting operators like the conserved current, which is the network charge of this global U1. I can extract the webs of these operators and the stress tensor of the theory. Now, if this generating functional happens to be invariant under gauge transformations of the external gauge field, then you can pretty quickly write down some word identities for non-conservation if you have sources, and this chart scalar for the current, and similarly for the stress tensor of the theory. This is all from the microscopic point of view. However, if you are only interested at really long wavelengths, what you can think of doing, if you are far away from the critical temperature of the system, is that you can think in the following way. So if you look at the VEV of your chart scalar, that comes together with a phase, and unless you have deformed the theory in a way that you break explicitly this U1, then it doesn't cost anything in terms of free energy in order to rotate this scalar. And this is really, I mean, you rotate it everywhere, globally on your space. Now you can imagine that this phase can vary very slowly in space-time, and that you can think that this will give you some kind of small, slow mode in the system. So what is the whole point of hydrodynamics? So you want to express this, well, the VEV of the stress tensor and the conserved current in terms of temperature, some unit normalized fluid velocity, the chemical potential, and if you are in the superfluid phase, you want to express this in the derivatives of this theta, which is also called the superfluid velocity. Then you can start counting variables, and you can see that this system of conservation laws is closed. And moreover, if you are in the superfluid phase, there is what is called the Josephson relation, which is basically telling you that the chemical potential is related to a time derivative of the phase of the superfluid. So, I mean, you can understand this just from thermodynamics. Well, in thermodynamics, AT is the chemical potential. You want to form a gauge invariant combination. So this combination is going to be a gauge invariant quantity. This is all nice, but I'm going to do something much simpler today. So I'm going to basically completely ignore what's happening with the stress tensor. Remember, I will be looking at effective theories, and there you can do pretty much anything you like. And from the microscopic point of view, you cannot just ignore that there is some stress tensor in the theory, but you can say that, oh, I'm interested to look at for example, the sector of the Goldstone mode and the coupled conserved current, and you can just focus on the dynamics of this sector. Then, of course, you would have to take into account the fact that there is some stress tensor in the theory, and this way you can start building bigger and bigger theories. Okay, so if I just focus now on the normal phase, so what I would write down for the current, there is only the chemical potential, there is no temperature, well, there is no dynamical temperature, and there is no dynamical fluid velocity. Well, what would happen at leading order in variations of the local chemical potential is that variations of the conserved charge would be proportional, would be variations of the chemical potential times the susceptibility. If you start having space-like variations of this chemical potential, you know that you will have to have some currents that will want to bring you back to thermal equilibrium. So those currents will be opposed to the changes of the chemical potential. Now, if you plug these expressions into the conservation law for the current, you will find some mode which is diffusive mode. And right. And that's it. There is nothing else there. Now, if you go to the superfluid phase, you basically write down something similar to the normal phase, but you will have to include the fact that you have the supercurrent. And this is telling you that even with a zero electric field, if you start from a finite external, vector field, and you start reducing the frequency to zero, even though the external electric field will go to zero, you will still have some current in your system, and this is the supercurrent. there is still this relation between mu and theta. Mu is theta dot basically. So if you plug these expressions in the conservation law, you will find something like that looks like a sound wave with a very specific speed of sound, and there is also some dissipating part. Now, more importantly, well, equally importantly, you have a new transport coefficient, this lambda naught. M is called the incoherent conductivity of your material, but when you're looking at, when you go to the superfluid phase, there is a new transport coefficient that shows up. And you might wonder, how can I go from that to that? Well, I mean, this current susceptibility actually goes to zero as you approach the critical temperature, right? So you go to the normal phase. This part goes away, so you recover that part. However, what happens with this zeta tria, which is called the third bulk viscosity of the superfluid, is that it actually blows up. Okay, it doesn't go to zero. If it went to zero, then you would say, okay, from this I'm getting that, from this I'm getting that, so I'm back to the normal phase. However, this is not how things work. This zeta tria actually blows up. From the holographic point of view, the product of chi jj with zeta 3 remains finite. This mode looks all fine. There is nothing funny happening with this mode, but your hydrodynamic expansion is actually breaking down. Okay. So why is this happening? So we said that in this order parameter, there is this phase that you take into account. But when you move away from the critical temperature and you actually write down these equations, the amplitude of this order parameter is frozen. Okay, it doesn't do anything. And at long wavelengths, at least. So there is this mode which has to do with the amplitude oscillations, but it is far down in the complex plane. Okay, if you think of poles in the complex plane. So when you wrote this theory of hydrodynamics, you have basically integrated out this degree of freedom. Okay. Now, as I'm approaching the critical temperature, this mode wants to join the rest of the hydrodynamic modes, which are very close to the origin. And you have one more mode that you have integrated out, and it becomes gapless. And that's a problem. You expect your effective theory to break down, and you see this by, I mean, through this zeta 3 blowing up. Okay? So I want to examine now theories which actually take into account, which are closer to this region, and which actually take into account this extra gap mode, which has a tiny, small gap. Okay.
So I should think of this zeta 3 as some kind of analog of no, but when the fact it blows up at TC is because really he wants to resolve the fact that there's a mode that's becoming long-lived.
That's exactly correct. So yes, yeah. So I will later on I will show some. There is some nice equations.
So this zeta 3 will like broaden out.
Exactly. Exactly, as you move away. So let's see, I mean, from the point of view of just thermodynamics, what's happening in the system, and that will be pretty telling if you want to make the further step of looking at dynamics in these systems. So I mean, it's good to write even there, even in thermodynamics, effective theories. So you basically come up with something that you call an order parameter in your system, and you say that there is some UV cutoff in your theory. Okay, you look down to very specific wavelengths, and you have integrated out everything else which is gapped and which is pretty boring in your system. Then you say that there is some energy functional, W naught, which is the free energy functional, and you write down some Boltzmann type of distribution, and which gives you the probability to have specific configurations in that order parameter. Then you can write down some partition function after integrating over the order parameter of your system, and free energy is what you would call just the log of this partition function. Okay, so W naught can be expressed in terms of some local density, and this is what we call the Ginzburg-Landau energy potential. And so crucially, so you have a term which gives you more free energy if you're higher free energy. If the order parameter depends on space-like configurations, you might expect that this will be suppressed because you have this positive term here. There is a quadratic term which goes to 0 exactly at the critical temperature. And there is a quartic interaction term which will play an important role. So this this free energy, I mean, the parameters that you see here will actually depend on the temperature because I have integrated out other degrees of freedom. So I have written down some theory of which the parameters depend on temperature. So as I'm going past, I mean, in the context of mean field theory, you might want to extremize, you might want to find the most probable configuration of this distribution. So you might want to extremize this W naught. And the extremum is basically given by something which is just homogeneous, right? There is no X dependence, there is nothing too fancy happening. And when you go down below the critical temperature, you find a non-zero value for the expectation value of this order parameter. Now you plug in the solution back to your free energy, and you find a second order phase transition. However, you might want to go beyond this, this approximation of the extremum of your free energy functional, and you want to do what is called the Gaussian approximation. So you basically expand quadratically this free energy in fluctuations. You can quite easily do these integrals, it's just Gaussians, and then the free energy will be given by the free energy of the most likely configuration plus corrections coming from the fluctuations. And what you will see is that as you approach the critical temperature, the free energy does get contributions from this. Well, this is the discontinuous, well, the heat capacity gets contributions from this. Heat capacity is the second derivative of the free energy, so you will get a discontinuity in the heat capacity. But what comes from the fluctuations will give you actually divergence. Okay, so fluctuations become, even in this model, simplified model, become very important close to the phase transition. So I told you all this just to emphasize that interactions become important, and you need to start renormalizing this probability distribution in order to find the correct fixed point. Good. So now, how about dynamics? So when you start thinking of time dependence in these models, you want to start by writing some equation. Okay. So how does this equation look like? Well, let's start from something which is 0 when you are in thermodynamic equilibrium, right? So this is, this is external sources for your thermodynamic variables. And this equation would be just, standard thermodynamics if you are in equilibrium. The derivative of the free energy is equal to the sources. And for the case of the order parameter that we looked at before, we actually set this external source to 0, and we looked at the extreme of this. So this equation is telling you that if you introduce a suitable kinetic coefficient, gamma naught, which you assume that remains finite as you approach the critical temperature, then whatever deviation from thermodynamic equilibrium, that will start driving your fields towards it. Okay? This is all classical. However, we have integrated out all these fast modes, which are still in the game, and now we are doing dynamics. And if you assume that all the fast modes that you have forgotten in your system have relaxation times which are much bigger, much smaller, faster relaxation rates than the natural relaxation rates that you discover from here, then you can say that I am okay with thinking of these extra modes, these fast modes, as being Gaussian noise. But there has to be this separation of scales in order for this to work. And since we discussed renormalization, well, you see, normalization will also be important here. It works in a slightly different way. You have to integrate out fast modes. you have to express them in terms of the noise, then you take the correlation functions of the noise and you start killing basically all your UV modes. But as you kill UV, more and more UV modes, you start killing modes whose relaxation rates are slower and slower. So this, at some point, you expect this will start breaking down. Okay? Now, this is the motivation to do things at a more advanced level. Good, so here I just looked at some scalar order parameter. There is no currents in the system. You might be worried that this time evolution, for example, does not conserve charge. It does not conserve the energy of the system, and in general, it doesn't. So you will, okay, sorry. There is one more thing to say. Yes, so there is this Gaussian noise, okay, which has zero expectation value for the fields theta, and these are the only non-trivial correlators, and 2-point correlators, which are proportional to some delta functions. And there is some constant d here. And I want to tell you how you fix this d, because it's important. So this is a stochastic system, right? So, I mean, the values of your distribution will follow the values of your fields will follow some distribution, some probability distribution P. So you can recast this stochastic system in terms of the probability distributions that these variables phi I will satisfy, will follow. And there is a certain equation that you can write for this functional P. And this is called the Fokker-Planck equation. So you basically want, independently of the initial conditions of the system to always relax to the Boltzmann distribution, right? So you can think of this as a current in field space, and this current has to be basically trivial exactly at the Boltzmann distribution. So that is going to, so D is the width of the noise fields, this one. And if you want to basically find the correct Boltzmann distribution with the right temperature, this D has to have a very specific value. Okay, and that guarantees that you will always relax to your correct thermal state. And now, if you go a bit more advanced, not more advanced, I mean, what also this choice guarantees you is the fluctuation dissipation theorem, which is not guaranteed just by writing this. Right? This didn't come from any path integral, it didn't come from anything field theoretic. I just wrote some equation, and I want to make sure that I'm relaxing to the correct probability distribution and that I satisfy the fluctuation dissipation theorem, which you would like to call.
Like to call this equation, the one in the previous slide.
This one?
It is valid only for small fluctuations around the equilibrium position.
And there is some counting that you have to do. And so it depends really on what this W naught is. But yeah, it has to, it is valid, yes. That's the basic assumption. But you're also saying that fluctuations are big in a critical point. Mm. So these are all good reasons for improvement. I'm not saying no.
Does it always have to be linear in T? I mean,
over here?
Yes. Why is it linear in T? I mean, we know of other scaling symmetries.
Well, you want this basically to be, okay, you could have second order terms, but you want this to be.
Well, it could even start dt to the z. Why is it linear in T? I mean, I've got a picture of quasi-normal modes that would tell me it's going to be linear in T, because I take some quasi-normal mode. Say we have some branch cut or something.
Well, you think that you're doing some kind of analytic expansion, right? Okay. And that's the whole point of renormalization. So you are doing the wrong expansion, but then you would have to find the actual fixed point that will give you these powers of z. So if you start doing renormalization and you identify the correct fixed point, yes, then you will start getting all these critical exponents you are talking about. Okay. That's the same thing with expanding the Ginzburg-Landau thing. In terms of power of psi, why does it have to be powers of psi? Well, it's not, but this is what you know how to do. So you have to renormalize. Okay, so now I want to start including, I'm running out of time. So I want to start including conserved charge, and so I have to write down something more complicated. Okay, so let's imagine now that this psi is the order parameter I'm interested in. What do I know about the derivative of psi? Well, if W naught is the energy, the free energy potential at fixed charge density, then I know that I have to satisfy some kind of Josephson relation, right? So the time derivative of the phase of psi should be proportional to the chemical potential, right? So this derivative of the free energy with respect to m, which is the chemical potential, that part is basically the Josephson relation. Okay? Now, I don't want this to change the value of W naught as I'm doing my time evolution, so I have to also include some term in the equation of motion for m, of charge density, such that during this time evolution, the value of W naught will remain constant. Right, so this looks very funny, I know, but we will try to understand, to make sense of this equation, which is the conservation law for the current, as if it was a word identity, as if on the right-hand side, I had the divergence of the current, right? Plus terms which have to do with the sources for psi. Now, I want to tell you that as opposed to the previous case where I had gamma naught was some positive real constant. Gamma naught here, the kinetic coefficient can be complex. It is allowed to be complex. The imaginary part of gamma naught will not give me any dissipation, but the real part of gamma naught is actually going to give me dissipation in this system. So how can I understand this second equation as a conservation law? So first of all, I'm going to write this W naught as a density in terms of some function of f, in terms of some function f, which is function of psi and the derivatives of psi. Now, this is going to give me two terms when I vary W naught with respect to psi star. So there will be terms of f that depends on the derivative of psi. And this term here will give me the chemical potential, right? So the derivative of W naught with respect to m is the chemical potential. So I can write this equation as the divergence of some current. So the first term will be what we call diffusion in hydrodynamics. The second term will give me the supercurrent, which is given in terms of variations of the free energy. And this last term here, sorry, bless. And this last term here is basically the scalar source. The derivative of the free energy with respect to psi is a scalar source, which is the terms that we found in the word identities. So these two equations will basically give me all I need to describe, to have current conservation, Josephson relation, and amplitude mode dynamics. So yes, for all these reasons that we discussed before, I would like to be able to go beyond Gaussian modes. Right? So if you want to describe interactions of the order parameter with fast modes, you want to describe higher derivative corrections in these laws, and you want to do it in a consistent way that it will give you basically, that it will know about the underlying thermal state, and that's non-trivial. So in the case of these simple equations that we wrote this Fokker-Planck equation, and we fixed these constants quite easily. And if I write something more funky, I mean, it will be much more difficult to make sure that there is an underlying thermal state in this. So for this reason, I want to rethink of this problem in the context of Keldysh-Schwinger formulas. Okay, so now I will tell you about the construction we have with Polydoros in Keldysh-Schwinger. Hopefully one day we'll publish this. Right, so in Keldysh-Schwinger, you start by admitting that if you have a generic density matrix, then time evolution will have to happen on a closed time path. And if rho minus infinity is the vacuum, then you can just forget about the second half of the backwards time evolution, and you can just stick with a forward time evolution, and it's the usual thing that you find in vacuum field theory. Now, since the time evolution is closed, I can start thinking of putting operator insertions in various points of this closed time path. And I can also write a generating functional, which will give me these correlation functions. If I go to the interaction picture for the sources O1 and O2, I can quite easily, I can write down some generating functional. And this generating functional will carry a lot of information, all the information I want to know about my field theory. So it might be more natural or more canonical to write everything in terms of this O1 and O2, which are fields defined in the forward time evolution branch or in the backwards time evolution branch, but it will be more convenient to define what is called the OR, the R, and the alpha bases, both for the observables and the source fields phi1 and phi2. Okay? So if you manage to compute this generating functional, you start taking derivatives with respect to the sources, and that will give you a lot of information through correlation functions. It's not just about the recursive correlation functions of the system. It can give you correlation functions with various sources and higher point correlation functions. So if I now focus on the thermal state, this was for a general initial state. If I focus on the thermal state and I try to write this generating functional in terms of the path integral, then I can do it. In the exponent, I will have the difference of the actions, and then the time path integration contour will also acquire, and you have to move down in the complex plane. That will give you the finite tangential path. Now, right. So what do the fields have to satisfy? So my fields will have to satisfy some gluing conditions. So at t equals infinity, psi1 and psi2 will have to be the same thing. And also, since I'm taking a trace, I have to make sure that psi1 at this point and psi2 at that point will be the same state that I'm integrating over. Now, what this is telling me is that if my original theory, my macroscopic theory, had some symmetry group G, which is local, then this symmetry will become G times G. Why? Because by having something local in time, I can preserve these gluing conditions. If I have some time-independent symmetry, then, and I want to preserve these gluing conditions, right? So I can only keep the diagonal part of this time-independent symmetry. I don't want to call it global. I want to call it time-independent. Good.
Sorry, can you explain that again?
So if I have some local symmetry group, I can just start doing, field transformations on this branch, field transformations on that branch, but I can just make sure that I'm not transforming the endpoints, precisely because the symmetry is time dependent, and so we'll be satisfying these equations, these boundary conditions. Mm-hmm. If the thing is global and I do here a different transformation from what I'm doing here, then I'm breaking these conditions. Okay, so if the symmetry is time independent, then I can only keep one copy, the diagonal one, which is transforming the one and the two fields in the same way. Okay, so this is all from the microscopic point of view. If you have your favorite action, you can just take it, plug it in there, do the integral, and that's fine. However, we are interested in effective theories. And what you have to do in that case is that you have to basically identify your effective fields. You have to introduce some UV cutoff and integrate all the high energy fluctuations. But as you integrate this, as you do this higher frequency fluctuations, you will end up with some effective action for your effective fields Chi1 and Chi2. And because of this integration, you cannot write this effective action as just the sum of two actions, right? You have integrated stuff, everything will become much more complicated. Now I want to write down some constraints that you get from unitarity. So you do get constraints by asking that your theory is unitary. And don't focus too much on this. You will get some constraints. Now I want to talk about an additional symmetry that your effective theories are going to have. So If your microscopic Hamiltonian was invariant under time reversal, and that's the most important part, then so would be your thermal state of your system. And you can also say that you can have some other discrete transformation which keeps the Hamiltonian invariant. Let's say parity. That's quite convenient. So if your microscopic theory had these symmetries, then you expect the effective theory to be invariant under what is called KMS transformations. And if you pick a particular product of these two discrete symmetries and you call it theta, then the KMS transformations, which I'm not writing here, it's something very specific. But if you take what is called the semi-classical limit of the effective theories, then the KMS transformations have this form. Okay, so the R fields go to R fields, but the alpha fields go to alpha fields plus time derivatives of R fields. What you also know from these constraints is that if you set the alpha fields dynamical fields to 0 and the alpha field source is equal to 0, that your effective action vanishes. So you want to expand in powers of these alpha fields, right? So the leading term will be a linear field in your alpha fields, and then you can package quadratic terms in alpha fields and so on. However, if you want these terms one by one to be KMS invariant, precisely because these are the KMS transformations, this L2 will also have time derivatives of the R fields, so that you can make the whole thing invariant. So what is the simplest thing you can write down in terms of these effective theories? So this L1, you can show that if you want it to be invariant, then it better be that L1 is a combination like this. So you have your alpha fields and your alpha sources, and the coefficients that multiply them can be written as functional derivatives of some functional s. Okay? And now this s, you can write it as a function of f, which is a function of your fields, your sources, and also of derivatives of your fields and your sources. Well, it turns out that this f is actually the Ginzburg-Landau free energy density, I found. It is the analog of what we wrote for the Ginzburg-Landau free energy, but now in the context of Kelty-Schwinger. Now, the simplest thing that you can write for L2, it's just some quadratic term in your field with no big dependency here. You could think of interactions and other more fancy stuff, but this is actually the simplest thing you can write. And also unitarity wants to impose that this constant C will be negative. C will also have to be real, and you better combine it with the time derivative of chi so that you can make the whole thing KMS invariant. Okay, so that's the simplest thing you can have. Okay, so let's use this as the first approximation to our system. Let's keep everything quadratic in the alpha fields. And let's go back to the effective action. So if you write down the effective action, you have the linear term in the alpha fields, and you have the quadratic term in the alpha fields. And you can integrate over the alpha fields by doing what is called Legendre transformation of the field chi alpha. And you can introduce the field theta, which actually looks like it wants to impose the classical equations of motion plus an oyster. Okay, so you have plus this theta that we had before in Hohenberg and Halperin, or in the original statistical physics systems, times a probability distribution for this theta, which happens to be Gaussian. So the width of this probability distribution actually came from this coefficient, and that was fixed by KMS symmetry. If you remember, when we were looking at statistical physics, we did a bit of hard work. We had to make sure that we were relaxing to the thermal state. But here, Kelty-Schwinger actually knows about the thermal state, and it implements all this on its own. I mean, automatically, it's built in. Okay, this is what you will call model A. It is the analog of the first system that I wrote with this scalar order parameter. Now I want to come with another model for charge diffusion. This doesn't have to do with phase transitions. It is an effective theory which describes the long wavelength dynamics of charge diffusion. So basically, I want to get the normal phase hydrodynamics that I discussed in the beginning, just through that, plus noise. So now I'm talking about charge. The effective action should be invariant under gauge transformations of the external fields. And the minimum dynamical degree of freedom that you can think of is just a scalar which also transforms with respect to this gauge transformation of your external fields. And you can actually start building gauge invariants, right? So if I add this gauge field with a derivative of this phi, of this scalar field phi, then this vector is gauge invariant. Okay, so it is a good starting point for my effective theory. Moreover, if I take the time component of this gauge invariant field, I can identify the chemical potential of what will be the chemical potential of the field. Good.
So can you go back to the slide before?
Here, yes.
Yes, so this parameter C is like what you call gamma or C.
Oh, in this case, yes, it will be gamma naught.
Gamma naught. So
that's the kinetic coefficient.
But if gamma naught goes to 0, now it seems to indicate that you cannot integrate out the chi alpha.
That's right, yes. So that's an assumption. That's an assumption. And that has, I think, in the 70s, there was big debate of what was happening with this gamma naught. Gamma naught could be an operator. Why does it have to be? Why does it have to be a number? Yes, that's an assumption for model A. That gives you different universality classes.
But in fact, in general, you get something non-local. That you get some memory effect from this, right?
Well,
this is a big assumption.
There is an assumption that you are looking at slow time derivatives. You are looking at that really long wavelength. And then when you start considering interactions with your noise and everything, then you start seeing UV features.
So this is already giving you the integrators over.
Exactly, that gives you the vanilla thing. I mean, the simplest thing you can possibly write down. So if you can think of looking at interactions of this, and that will give you corrections. And people have looked.
Yeah, because this what actually these are they're basically green functions, some green functions of the stochastic.
Yes, exactly. Okay, so let's go back to diffusion. So if I'm in the normal phase, I want everything to be expressible in terms of this local chemical potential mu, and that gives me, some extra symmetry. Which, sorry, Blaise. That gives me an extra symmetry, which people have called what? The chemical shift symmetry. 10 years ago.
You can just close the.
Okay. Extra. So there is some funny symmetry in this funny symmetry, nice symmetry. There is some unusual symmetry which basically shifts the R fields by time-independent gauge parameters, and it leaves the alpha fields invariant. This has to do with the fact, that this symmetry is time-independent, and it has to do with the discussion I had before. So you can only keep the diagonal part of this symmetry, and this is telling you that it is only the R fields that transform under it, but not the alpha fields. And the gauge transformation is time-independent. Okay, so if you are describing the normal phase, your theory better have this symmetry. So in this case, the leading term will be what? If I take the derivative of f with respect to the chemical potential, I will find the charge density. There is, I'm not the one who did this. Yes. Okay. You will have the charge density, and then you have to start counting derivatives, and time derivatives scale like epsilon squared, space like derivatives scale like epsilon. And if you are consistent with what you want to keep in the derivative expansion, And then you can write down basically this model. And because this model has a shift symmetry in the alpha field, phi alpha, that will give you another current. And you can see from what I'm writing here that this is indeed the normal phase of hydrodynamics that we discussed before, plus some noise. Okay, it's not just classical hydrodynamics. So you have the diffusive current, you have the charge density, and you get something more, much more interesting. So how am I going to obtain now what is called the model F? So now I want to take the complex order parameter, and I want to couple it to this diffusion theory. Okay, I'm very close to the critical point. So my effective theory, and this is what we actually did with Polydoros. So you need some complex order parameter psi I, and you also need the normal phase charge, the phi I, which parameterizes the normal phase charge density. Now, you want this theory to be Gaines invariant after under gauge transformations of the external Maxwell field. So basically, your fields are going to transform in this way. Okay, so I have linearized. I have defined what I have called the diagonal gauge parameter, which is lambda 1 and lambda 2. If you do a gauge transformation both forward time evolution and backwards time evolution, you can define the diagonal gauge parameter. You can define the anti-diagonal gauge parameter lambda alpha. You are focusing, you want to keep the size of the alpha fields small because they carry quantum correction. So I'm focusing on small anti-diagonal gauge transformations, whatever that means. And I have also included the chemical shift symmetry for the scalar field phi. Okay, so I want my theory, my effective theory, to be invariant under these transformations, under lambda alpha. Remember, lambda alpha is, the gauge transformation is local in time, so I can keep two copies. So my theory should be invariant under both diagonal and anti-diagonal gauge transformations. But the theory should only be invariant under the diagonal part of the time-independent gauge transformations. So these time-independent gauge transformations, they have nothing to do with the gauge field, right? It's just a redundancy of the theory because I wrote my chemical potential as a time derivative of some field, of this field phi. Okay, so instead of working with these variables, which are gauge dependent and they transform under gauge transformations, I can define gauge invariant variables. I can take advantage of the fact that phi rho, phi r, gets shifted by a diagonal gauge transformation, for example, and psi r is just rotated, and I can form this combination, which is just gauge invariant under external gauge transformations. Right? So I can come up with new complex scalars and vector fields, which are basically invariant under the external transformations of the external electromagnetic field. However, if you do that, then you see that the chemical shift is actually becoming a gauge symmetry of the order parameter, right? So I'm trading the electromagnetic gauge transformations, but now this is telling me that what I basically want to do is I want to take the diffusion dynamics, the theory for diffusion dynamics, take model A with a complex order parameter, engage the symmetry, the global symmetry of model A with the chemical shift symmetry. So now I can define covariant derivatives which have to do with this chemical shift symmetry. The field B will be the gauge field of this gauge symmetry. And for the time component of this covariant derivative, it's just partial derivative of the complex fields. Now, what can I write down? Well, again, for L1, the linear term in the alpha fields, it will be some derivative of some functional S with respect to the R fields multiplied with the alpha fields. And I can also introduce some source terms here. So this source SR transforms in exactly the same way with the parameter. And this combination is just invariant under chemical shifts, gauge transformations, and also it is KMS invariant. So now I have to write something down for this S, right? So this free energy density, and you basically write down the most general thing you can think of in terms of gauge invariant quantities, up to some order in derivative expansion and powers of fields. Now, for the quadratic part of the Gelder-Schwinger action, you can write down something pretty fixed. I'm doing just a minimal thing, right? I'm not doing anything fancy, no interactions or anything like that. And you can have, I mean, the psi alpha square term, and you can have the b squared terms, the alpha square terms, and then unitarity tells you, well, unitarity tells you that this C6 R will have to be a real number. However, here this C6 can be complex, like you are allowed to have a complex number. And this has to do with the fact that this gamma naught could be complex when I was describing model F in statistical physics.
So here, what determines whether a given coefficient is complex or real, or like you decide? Because you're saying C5 has to be real.
For example, yes. So the imaginary part of, well, it has to do with these properties.
So for instance, the first one will kill the imaginary part of some coefficient.
Exactly. Okay. And then the last one will tell you whether you have something positive or negative.
Okay. There might be more conditions imposed by unitarity that we don't know about, so like in the bootstrap product.
Like what do you have in mind?
Well, these are naive, direct consequence of unitarity, but there might be some hidden.
Something more hidden.
For example,
When you start looking at actual correlation functions.
Right.
Yes. No, this is just looking at the generating functional, the most basic unitarity conditions you can write down.
But if you have higher point correlation functions, you need to include higher order terms in that Lagrangian, and so it's not, your constraint would probably also involve the coefficients of these higher order terms. And then it's not clear that they can then constrain the lower order terms.
If they're positive, if you get something squared,
right.
Well, at this level, I don't think you can choose anything out of higher order correlation functions. But if you write something more complicated, then maybe.
It's like, you know, in hydrodynamics, when you impose positivity of entropy dissipation, of entropy production, the higher you go in derivatives, you can get constraints that involve the lower order coefficients, but those constraints don't.
You're saying that these will constrain the higher order coefficients?
Yes, yes. And if you set those higher order coefficients to 0, then usually those constraints don't further constrain the lower order coefficients. I don't know about the bootstrap, but that was.
And the bootstrap, it seems to work with energy. Okay.
Right. Where was I? Here, I think. Right. However, C6 is allowed to be complex, but what you will have in the term that makes this KMS invariant is just the real part of C6. Okay, and the only constraint that you get is for the real part. And once again, there is this translational you can do shifts in the phi alphas, and that will give you another current. And again, the another current is exactly what you would get from the model F equation. So yes, you would like to show that this is actually equivalent to model F. So you do Lysander transformations for both noise fields, psi alpha and phi alpha. Also, the energy potential that I have written down here is a fixed chemical potential. What Hockenberg and Halperin have written down was a fixed charge density, so you will have to do a Legendre transformation between the two energy potentials. And you can identify C6 with the 1 over the complex conjugate of gamma naught in model F, and C5 is just the incoherent conductivity. And of course, the stochastic equations will also match at this level. So this is the matching with model F. So now I want to do something else. Now, if you look at this potential, right, so there is some minimum value. You can minimize it by taking a minimum value for, by taking an appropriate value for this psi naught. So you can think of doing a semi-classical integral or expansion of your effective theory, and then doing the path integral around fluctuations around this semi-classical minimum. Now, if you do, and if you look at modes of just the free theory without anything too fancy, you will basically discover a gapped mode, which is the gapped mode we are after. That's the gapped mode of the amplitude, and you will also find a couple of sand modes. Okay. So what I want to do is to basically say that the gap of this gapped mode is beyond my UV cutoff, and just integrate it out. And then I should end up with a superfluid, right? So if I integrate out the gapped mode, I'd better find the superfluid theory of a superfluid. So we did that with Polydoros, and you can integrate over, the radial part of the order parameter. You can integrate over alpha fields. You can integrate over this phi r fields, which give you the dynamics of the charge density, the normal phase charge density, and you basically end up with this. Okay, so now C is a new vector field, which is written in terms of some derivative of some phase phi plus the external gauge field, and this is gauge invariant. Now, if I compare this with something specific that Blaise, Luca, and Varus have written maybe a year ago or so, that reproduces exactly superfluid hydrodynamics, right? And this zeta 3 coefficient can be expressed in terms of the bare constants of the previous theory times 1 over the gap. Okay, 1 over the gap of the Higgs mode. This is the gap of the Higgs mode. And so
wait, here kappa 0 and u0, they're the coefficients in the Landau-Ginzburg action?
That's right, yes.
And
where is it? Yeah.
Okay. And then chi-d and chi-n?
You said chi?
So, I think if you go back to your expression for zeta 3.
How about that?
This chi-n here.
Yes. This
one.
one.
Both, before you had, I think, chi-n in the normal phase and
yes.
chi-d in the superfluid phase.
Yeah. So the susceptibility changes, right? And so this chi-d is not the same thing with chi-n. It is chi-n plus a term. I think it's U0 squared plus something.
Okay.
Because, I mean, all these constants can be expressed in terms of the bare constants of the Landau-Ginzburg.
So here you're saying there's a relation between chi-d and
I'm only highlighting this equation. Chi-jj, for example, yes, it can be expressed. The current susceptibility can be expressed in terms of the Ginzburg-Landau parameter.
So is it completely clear that this thermodynamic factor that multiplies 1 over the gap can never vanish at TC? Okay, so by assumption, so this, if you want to have this transition, you not better be finite. Right? So it's it's the coefficient multiplying the quartic term. Yeah.
Okay. Let's go one by one. Chi-b, well, that's the susceptibility.
Yeah. Is it this one term that will remain one?
Which one? C6 by assumption is finite. I mean, this whole thing is assumed to be finite from the very basic assumptions. This is why I chose to write it this way. So the only thing that goes to zero, the only thing that goes to zero, close to the transition is the gap.
The reason I'm asking is because there are cases where both the gap and the susceptibility is to zero. So that's, in fact, zeta 3. I mean, anyway.
The gap, and this is holographic.
Yes.
Yeah, I mean, the product of chi jj over omega gap in holography goes to zero, goes to something constant.
Yes.
But in general, I think there is, I'm not aware of an argument which tells you that chi jj and the gap should go to something finite. You would need some scaling argument, which I'm not sure there exists. Yeah, this
KJJ is the superfluid density, right?
That's right. With it is proportional to the superfluid density, yes.
So it has to go to zero at the gap.
Yeah.
At the TC.
Yeah, that for sure goes to zero.
Yeah, so it's not holography.
This is in general.
Yes.
However, the ratio of chi jj times divided by the gap goes to something finite in holography.
But you can't prove from mean field theory that they need to go to zero.
Mean field theory, yes, or mean field theory. But I'm not sure you can trust mean field theory here.
Close to TC?
This is when you cannot trust it at all. Okay, so yes, we have this fancy system. Right. And you might wonder what's happening if I just ignore, if I treat it as a classical system, forget all about noise, and do actually the mean field theory thing. And that's basically what describes holography. So I will be hopefully very quick about this.
You've
been
going on for an hour. Closing time is 15 minutes from now, including questions.
Okay, so this is my closing time. Okay.
No, you can go on for a little bit, but keep some time for
I think 10 minutes. I think 10 minutes should be enough.
Sounds good.
Okay, so the vacuum of CFT in terms of holography is just ABS. I don't want to say too many things about that. You can deform your CFT by introducing sources, and sources on the gravitational side basically correspond to deforming the boundary metric of ADS. You can couple your theory to an external vector source, and this corresponds to boundary conditions of your bulk gauge field. And you can also introduce source terms that correspond to scalar operators, and that's again boundary conditions for the bulk scalar fields. And now in the large n limit, or well, in the classical limit or in the semi-classical limit, what holography tells you is that actually the partition function of your CFT is becoming the classical partition function on the gravitational side. And so if you start taking derivatives of your partition function with respect to these external sources or with respect to the boundary conditions, that will allow you to compute vacuum expectation values of operators, which is pretty powerful. Now, I want to write a holographic model that is dual to this model F. So I'm forgetting about fluctuations of the stress tensor. I want to completely decouple it from the picture. And the minimal thing you can do in order to do this is to consider what is called a probe theory. And a probe theory does not interact with gravity at all. So that from the bulk point of view, the bulk metric is completely fixed. It has to describe the thermal state. But the ingredients I want to consider here is a complex bulk scalar field psi. That will give me the order parameter. I want to consider a gauge field in the bulk A nu, which will give me a vector source on the boundary. And I want also to consider some neutral scalar field that will introduce some scale in the theory and which can actually drive the phase transition. Okay. And so the background will be some fixed background black hole. And the scalar psi will become unstable below some critical temperature or below some critical value of this deformation parameter of the neutral scalar, and that will give me a new branch of spontaneously broken black holes. So how does this thermal state look like? So I have this scalar. I basically want to define these quantities. So this charged scalar takes in general some value psi h on this horizon, and the vector field does two things. So the first thing, from the boundary point of view, gives you something really meaningful from the field theory side. It allows you to set the chemical potential, but the flux of this of the field strength actually gives you the charge density of the field theory. Okay. Now we can define also the flux through the horizon. In general, this has nothing to do with the field theory side. If you are in the normal phase, you can relate the flux through the horizon to the flux through the boundary, through Gauss's law. However, when you are in the broken phase, this flux through the horizon has nothing to do with the flux of the boundary, right? So they are just two different things when you are in the broken phase. Now, how does the transition happen? Well, you imagine that you have some parameter space where these black holes, I mean, these are the parameters of your black holes. You can have temperature, chemical potential, the deformation parameter of this scalar phi s. And what I want to do is to follow some trajectory in this, in this parameter space, right? I'm not fixing any specific ensemble. I just want the transition to happen, and I just want to move somehow in this this parameter space. Now, so what I'm imagining is that I have this parameter zeta, which is parameterizing this curve, and that there is a critical value for zeta, zeta c, where exactly, at this point, zeta c, you have a static mode for this bulk scalar field. And as soon as you have a static mode for the bulk scalar field, then it becomes unstable for values of zeta smaller than the critical value. You just follow the instability, you construct the broken phase black holes, and these are supposed to be the holographic superfluids. So now you want to go ahead and study the modes around these backgrounds, right? So there is already a mode there, a static mode, which you have to take advantage of. So at exactly the critical point, you know that there is some static solution, okay, which is the mode that drives the phase transition. As you move away from the critical point, then this mode becomes the gap mode that you want to include in your theory, and you can start studying the dynamics of this amplitude mode by basically writing this static mode and expanding in epsilon. So epsilon is basically the order of your wave vector, and you start expanding the solution, right? So, and you want to find these corrections. How can you find these corrections? So you basically have to look at the equations of motion to make sense of this, but you have two branches of black holes. Okay, so you have the normal phase black holes and you have the broken phase black holes. If I take derivatives of these black hole solutions in the thermodynamic parameter space, I will get some static modes. That's static perturbations. If I start combining these static perturbations in a way that I satisfy now the conservation laws, which are active, when I was constructing the backgrounds, the conservation laws were saying nothing. They were automatically satisfied. However, when I start including space-time dependence, the conservation laws become active. And this is where I start needing the variations of the normal phase black holes. This will give me the parameters that will let me satisfy the conservation laws. So if you do all that, you can come up with an effective theory for these fluctuations. I'm not going to go into any great detail, but the dynamics of these modes is actually described by just model F without any noise terms. Okay, you just write down some equations like this with some parameters which are fixed in terms of your holographic theory. So the first line is parameters which have to do with the free energy. And it's no wonder that these parameters will be fixed by thermodynamic quantities. So this delta rho, for example, here is the difference between the charge density of the normal phase and the broken phase black holes at fixed chemical potential. Or Kjj is the charge susceptibility of your broken phase black holes. However, what is more important is that you can write down the kinetic coefficient, gamma naught, in terms of black hole data, and also this has been done years ago. You can also write down the incoherent conductivity in terms of the parameters, in terms of black hole data. Again. So this tau is a parameter in your bulk action. When you evaluate tau on the horizon, it will give you the incoherent conductivity. And the kinetic coefficient can be expressed in terms of, it is complex in general, and it will be the square of the value of the charge scalar on the horizon. And the imaginary part will have to do with the difference between the horizon charge densities and field theory charge density. Okay, so you are in the broken phase, this is non-zero, and you will also have a complex part. Now, if you are careful and you take the limit of all this as you take your system to the critical point, you will find that this gamma naught is finite. It does remain finite, at least in holography.
At the critical point.
At the critical point. So psi and the verve scale in the same way. Mm-hmm. Right? So that part will be finite. Rho is basically because the difference in rho and rho h is because of back reaction of the gauge field. So it will be again proportional to psi squared. Right? So this term and that term are of the same order as I'm approaching the critical point. The ratio remains finite. Okay, and the complex part, well, the non-dissipative part of gamma naught has to do with finite density. Now, maybe you can skip this, but I want to tell you, at least for neutral black holes, what's the story when you commute the order of small k with small distance from with small gap. So, right, for very small values of k of the wave vector, what you basically have is two sound modes and the gap mode, and that's it. Okay. Now I want to increase the value of k at values larger than the gap, and what happens is that these two sound modes approach the imaginary axis. There is some critical value for k when you have a collision, and now the two sound modes, they basically coincide. And then as you increase k even further, one of the two sound modes becomes the charge diffusion mode as you keep moving on the imaginary axis. And the other sound mode becomes the diffusive mode that you find for the order parameter just above the critical temperature. And the gap mode becomes the second diffusive mode of the order parameter. This, I think there is a difference with what had been said in the past about this, I mean, what becomes what, but I think it's pretty clear if you look at just model F. You convince yourself.
So these two, they have the same quadratic part.
Say that again, Les?
These two modes, they have exactly the same quadratic part.
Yes. So if you look at the order parameter above the critical temperature, because there is an O2 symmetry, there is one mode that goes like this, one mode that goes like this. That will give you double mode. Okay? So you would expect that if you commute the limits of k with t minus tc, this has to happen, because you want to recover whatever happens above the critical temperature. You are at very small lengths. And you get the charge diffusion mode with the correct susceptibility. Large k. This is just numerical checks of what I wrote. There is analytic expressions. So if you plot the real part of these sum modes, you divide by k. Then for k much smaller than this critical value of k, you basically get, yes, that omega plus and omega minus grow linearly with k. There's just two sound modes. And above the critical value, you don't have any real part for these modes. And if I divide by k squared, both modes have the same quadratic part. That's the diffusive part. And after kc, you basically have that omega plus and omega minus are proportional to k squared because this goes to the constant, but these are different constants, right? So this tells you that one will become the diffusive mode, the other one is going to become the scalar, the order parameter mode. So let me finish, I think I'm on time. So I rewrote the model F in the Kelder-Schwinger formalism. I tried to argue that the third bulk viscosity diverges close to the transition, just by integrating out the amplitude mode from model F. I told you that holographic nearly critical superfluids are just captured by the mean field theory version of model F. And things to look at in the future are, model F beyond Gaussian noise, and to also include the stress tensor in the description either by Kelder-Schwinger or by looking at holographic models, which involve also the bulk metric. Thank you.
Questions?
Very quick one. In the holographic model, why do you need the extra scalar? I mean, could you drive the phase transition by the charge scalar alone? Would you miss some features?
Good question. Why did we do that? You could do it, but I was very careful. Right. So in holography, you get some variations with respect to the chemical potential, and it's not, I think, entirely clear whether it is variation of energy or variation of free energy. So having this extra scalar distinguishes the two. I remember that was the reason. Yes. Okay, so in principle, you want to have many parameters, and you want to make sure that you have the difference of the energy, for example.
The bulk viscosity did you compute it from holography?
Yeah, yes. Well, in holography, here it is.
And this was the holography.
Well, you just plug in the holographic expressions for the constants. It's the same thing.
What if you don't take the small h bar limits in the Schwinger-Keldysh analysis?
You mean include quantum corrections?
Because it seems that this is what everybody does
yes,
in our
community,
right. But in principle, the point of doing Schwinger-Keldysh would be
I think
not to do that.
You're making some assumption that you are at high temperatures. Yeah, if you want to go to really low temperatures, you'd better not do that.
But when you were constructing your Schwinger-Keldysh actions, you were doing that very generally, right? The assumption that you were at high temperature was to TC, this came later.
But the form of the KMS symmetry, maybe?
Yes, so then the KMS symmetry does not look as simple as that.
Yes, it's not local in time.
Yeah.
It's not related derivative
of
the R fields.
Yeah, that will be more complicated.
Yes.
Much more complicated.
Yes, you probably cannot do a derivative expansion in the technical game.
Yeah. You probably have to keep all the powers of the A fields also, right? Because if you're in quantum, then
that's right. Yes.
You cannot expand.
Yeah. You cannot expand anymore in beta. Yeah.
Any other questions? No, then let's thank Aristoteles again.